Good morning, everyone. Today, I'm excited to share with you our latest work, boosting file system elegantly, a transparent NVM real-time log for disk file systems. I am Guoyu Wang, an author of this paper, and I am from Jilin University. So over the past decade, we have witnessed the rise of non-volatile memory, also known as NVM or PMAM. Among a large amount of research, NVM file systems have become one of the most popular research areas. And as we can see, various types of NVM file systems have emerged during this period, ranging from kernel space to user space, and from direct access to NVM to hybrid systems combining multiple storage devices. Well, indeed, NVM offers higher persistence performance and finer grain write support compared to traditional disk storage. However, NVM file systems are not silver bullets. Here are some problems with NVM-FS. First, NVM has limited capacity compared to disk. For example, Optane can provide up to 500 gigabytes per module and up to 6 terabytes per socket, while a disk array can provide petabytes of storage space. Also, redesigning file systems for NVM may introduce several inconveniences to users, like we need to copy data from the old disk file system to the new NVM file system. And the consistency semantics of NVM-FS is different with disk-FS, with a DRAM cache. Besides, a large amount of new code in NVM-FS may not be as stable as time-tested disk-FS. And from a performance perspective, although NVM is faster than disks, NVM file systems are not always better than disk file systems, because disk file systems are often accelerated by DRAM cache, while most NVM file systems bypass the DRAM cache. Let's take NOVA and ext4 as examples. As shown in the figure, for read operations, the disk-FS performs better than the NVM-FS when the cache is warm, and the NVM-FS outperforms the disk-FS when the cache is cold. Well, for write operations, the disk-FS with DRAM cache performs better than NVM-FS, while the NVM-FS performs better than disk-FS when there are synchronous writes. So to summarize, the advantages of NVM-FS are limited to, first, the read operations when the cache is cold, and second, synchronous write operations. For other operations that can be accelerated by a DRAM cache, disk-FS offers better performance. So here's a question. Can we combine the advantages of both disk-FS and NVM-FS? And I think the answer is yes. We can accelerate synchronous writes using NVM while retaining the fast path of a DRAM cache. And we believe that accelerating disk file systems with NVM is a good idea, but current efforts haven't achieved the best practice. SPFS accelerates disk file system by taking over some data to NVM through predicting sync events, but it fails to provide efficient acceleration in scenarios when sync operations are irregular or infrequent. After taking over the data, it may also slow down subsequent read and write operations. P2Cache allows fast reads from DRAM, but the cost is write performance. It writes all data, whether sync or async, to NVM. This clearly leads to a performance downgrade for workloads with async writes. And it is evident that these accelerators vaguely take over a large amount of data, rather than precisely accelerating only the slow synchronous operations. Additionally, due to the frequent need to access NVM data, SPFS and P2Cache must establish an index for NVM at runtime, which introduces complexity and performance overhead. Besides, they also require continuous and large amount of NVM space. So we found that two key points have been overlooked by previous work. First, DRAM cache already provides an efficient indexing and data retrieval mechanism. So therefore, NVM should focus solely on persisting synchronous data and should avoid the need of establishing indexes for NVM and retrieving data from NVM. Second, NVM writes and disk writes may interleave in a random order. Previous work has taken over all operations on a large amount of data to avoid data version inconsistencies caused by such interleaving. We found that clarifying the right timing relationships across different devices helps reduce unnecessary data and operation from being taken over, so that we can fully leverage the high performance of DRAM. We want to efficiently integrate NVM into the current system, and it should have the following attributes. First, it should be transparent to both the upper layer applications and the underlying disk file system. In this way, we can avoid requiring changes to user programs, and meanwhile, still reuse the mature disk file systems. At the same time, we can avoid the overhead of data migration. Second, we cannot compromise the consistency guarantees of sync operations in the disk file system. At the same time, there's no need to introduce strong consistency into non-sync scenarios, as this would only reduce performance. In addition, unlike previous work, we aim to ensure that there is no performance degradation to the existing disk file system under any scenario, whether it is a read or write, synchronous or asynchronous. Finally, we aim to design and implement a solution that is lightweight and efficient and occupies as little NVM space as possible. So this is our design. We designed NVLog. Unlike previous work, NVLog is not a file system, but it is a write-ahead log designed specifically for disk file systems. Similar to a write-ahead log on database, NVLog focuses on recording write events so that data that hasn't been committed to disk can be replayed after a crash. And we have all the advantages that a write-ahead log has. Well, unlike a database write-ahead log, NVLog does not record all data to be written to disk, as that would slow down the performance. Instead, NVLog only records the data affected by synchronous operations in order to bypass the slow disk I/O. So we intercept the sync writes at the VFS layer through VFS of sync range, leaving all other operations to be handled by the faster DRAM cache. And at the same time, we provide fine-grained data persistence and address the consistency issues caused by interleaving of NVM and disk writes. So, sorry. Before introducing the sync write steps on NVLog, I would like first to introduce the data structure used by NVLog to store data on NVM. NVLog adopts a log-based structure. First, the inode log are used to persist sync data for a file. For each write, the data is divided by page boundaries, and each part will be saved by an inode log entry, like the green blocks in this figure. And second, for each inode log, its head and tail are stored in a special superlog entry, which is the small blue blocks in the figure. And all the superlog entries together forms the whole superlog, and the beginning of this superlog is placed at the 0 address of the NVMs for the convenience of the recovery. Note that when the data is divided by page, its head and tail may not be page aligned, which could result in data chunks smaller than a page, while the middle part may consist of page aligned data blocks containing full pages of data. For the unaligned small data chunks, we use an in-place log entry to write the data at byte level within the log entry itself, like entry 0 and entry 3 in this figure. For the full page data chunks, we write the data to separate NVM pages and link them using an out-of-place entry, like the entry 1 and entry 2 in this figure, to make it easier for subsequent garbage collection. Here is the sync write step for a traditional disk file system. We can see that when sync happens, it needs to wait for slow disk I/O. And since the minimum write granularity of a disk is block, these operations cannot achieve finer-grained persistence. So instead of waiting for slow disk I/O, we write sync data to NVM in NVLog and immediately return. The pages will later be asynchronously written back to disk in the background. And note that for async writes, we know the offset and length of the data being written. And since NVM supports byte granularity writes, we can achieve fine-grained persistence for small asyncs. Here we further illustrate the correspondence between sync write process and log entries. As shown for async writes, the unaligned portions of the write are handled with an in-place entry for fine-grained writes, like the yellow parts. And the aligned full-page data is written using an out-of-place entry, like the red parts. For standalone sync costs, such as fsync and fdatasync, since we only know which pages are dirty at the time of the call, but not which specific bytes are dirty, we can only absorb the synchronous write at the page granularity. As the figure shows, now we know that in fsync calls, a small amount of this pink user writes can cause a large chunk of write data to be written to the storage medium. But since NVM supports byte granularity writes, could we make sync write fine-grained? Of course, tracking dirty state for each byte is not practical. However, we also know that in async writes, NVLog can absorb data with byte granularity, right? So from this observation, our idea is to predict the file's sync pattern and proactively mark or clear the async flag for each file. By this active sync mechanism, we can continue, when continuous small scattered sync writes happens on a file, NVLog can absorb most of them with a finer granularity. And since there are two different write paths, one from DRAM to NVM and another from DRAM to disk, so any interleaving between them could lead to consistency issues. In other words, if the order isn't known, some outdated NVM data might overwrite the updated data on disk during crash recovery. So our solution is to record the necessary disk write-back events on NVM, like the purple bubbles in the figure, to establish a global clock. And you can find more details in our paper, or feel free to ask me later. To understand the garbage collection process, we need to know which NVM records, or to say entries, are no longer needed. Since we split the data along page boundaries during writes, we can see that each entry corresponds to a single page. If there is an overwrite of the entire page, meaning there's an out-of-place entry, then all previous entries related to the page can be discarded. And alternatively, if a page has been written back to the disk, it means that all prior writes to that page are already saved, right? So the entry for that page prior to the write-back event can also be discarded. And after that, we just need to schedule a background thread to reclaim these unused entries and the associated data. And here are some examples. Like these out-of-place entries and write-back entries will expire the prior entries of that page. So as for crash recovery, we first need to identify all the relevant entries for each page. We perform a full scan of the entire NVLog, linking all the elements related to the same page into a linked list like this. And then we sequentially access each page and replay the non-expired entries onto the disk. So here's our experimental setup. Due to time constraints, I won't go into detail here, but note that all our evaluations are performed under a warm cache. Because on one hand, cache hits are the norm for most workloads. And on the other hand, we only accelerate synchronous writes, so we need to avoid performance interference caused by cache misses. And first, we tested the performance of multiple file systems and accelerators and their various read, write, and sync ratios. Our NVLog keeps DRAM's high performance when there are no sync writes at all, in which case we can outperform NVM file systems. Under full synchronous writes, it can match the performance of NVM-FS, and it achieves the best overall performance across all systems when handling mixed read and async write requests. The key reason for this high performance is that NVLog precisely accelerates sync writes, while allowing DRAM to process all other requests more quickly. Next, we conduct a pure synchronous write performance test. We can provide up to 15 times speed up to disk file systems. Under small sync writes, NVLog can even outperform NOVA by 4 times because NVLog supports fine-grained writes. Well, note that in the case of 16 kilobytes large bulk synchronous writes, NVLog performs worse than NOVA because NOVA only needs to write to NVM once, while NVLog has to write to both NVM and DRAM. However, we believe that applications that require purely large bulk synchronous writes are relatively rare. And therefore, sacrificing a bit of synchronous write performance for better async write and read performance should be worthwhile in a wider range of use cases. Next, we test the garbage collection performance. We can see that with the help of GC, NVLog only occupies a small amount of NVM space temporarily. And we also tested NVLog with real-world workloads. The results shows that under various tasks, NVLog can at least match the performance of the best among disk-FS and NVM-FS, demonstrating its broad applicability. And here's the conclusion of our work. We propose a new method to use NVM to accelerate disk file systems with transparency. By integrating NVM into the system as a write-ahead log, we can precisely absorb those slow sync writes to NVM while leaving other operations to DRAM. Such design ensures that NVLog never causes performance degradation for disk file systems under any circumstances. Besides, we adopted a lightweight design and implementation using only a small amount of NVM space. We believe this painless use of NVM is more likely to be widely accepted by users of legacy storage systems. And we recommend that users running write-intensive databases or similar applications that require lots of bulk synchronous writes to choose NOVA. Beyond that, for servers, PCs, and mobile devices with mixed read-write workloads, we believe NVLog holds greater potential. And finally, the prototype is open sourced on GitHub, and that's what I'm going to share today. Thank you.